Hello, good afternoon. Here we are yet again for another lovely session of ENGR 2302 Engineering Dynamics. Today will be the 17th lecture in the series, and we'll be continuing on with some of our topics from Chapter 17 of the Beer Vector Mechanics text. Continuing on with some applications of the conservation of linear and rotational momentum of rigid bodies. Now, we've gone through the theory of this last time, and today I want to work through a few examples. So today we're mainly going to be looking at a series of examples relating to this. Okay, so let us begin. The first example I will work through will involve a couple of gears. So let's draw this out. And as I am wont to do, I'm going to draw out the gears as circles, if we will, but maybe not draw all the teeth out on them. So example 1 for today. Consider a system where we have two gears of two different radii. And again, these are two perfectly circular gears. If it appears that they're anything other than a circle, those are just optical distortion from air currents in the room. Yeah, we'll go with that one again. Get a lot of mileage out of that one. Really wear that one out. Anyway. So there is two different gears here of two different radii. And yes, I'm not drawing the teeth connecting here because I'm terrible at drawing gear teeth, but these are actually two gears rather than two circles. Although if you want to think of them as two circles or two discs with surfaces that won't slip past each other, the dynamics would be exactly the same. As long as the one surface will not slip past the other one. So this is going to be B. And RB, the radius of gear B, is going to be 100 millimeters. And then RA, the radius of gear A, is going to be 250 millimeters. 250 millimeters, and this is supported by some support mechanism like this, and some support mechanism like this if we want. And I am also given this information about these gears. So I'll say two gears here. And then I am told that MA, mass of gear A, is 10 kilograms, and the mass of gear B is 3 kilograms. And then the radius of gyration of gear A, KA, is going to be 200 millimeters, and KB, the radius of gyration of gear B, is going to be 80 millimeters. 80 millimeters. And I'm also told the system is at rest when let's say a 6 Newton meter load is applied to gear B. A 6 Newton meter load is applied to B. And we may have looked at a similar problem previously looking at energy considerations. Today, though, we'll be looking at momentum rather than energy. When a 6 Newton meter load, or when a 6 Newton meter torque or couple or moment is applied to B. To gear B. All right, and then ignoring friction, so we're going to ignore friction. Oh, so that's one thing we're told. And also friction is negligible. Friction will be negligible, and find three things. Yeah, so this is very similar, perhaps even the same as a previous problem if I remember correctly. But previously we worked with, I think we actually worked through this problem before in a different way, but this time we're using momentum rather than energy. So find A, the time for gear B to reach 600 RPM. To reach 600 RPM. And B, the tangential force exerted by gear B on gear A. So the tangential force exerted on gear A by gear B. So this system here. And we're going to use, again, impulse momentum to solve this problem. And so let's see here. So we're going to draw our impulse diagrams again. And let us consider this. Let's say this here. I'm going to draw the initial angular momentum. Now we don't have any kind of translational momentum here, so I'm not going to worry about that. The disks, both of these disks are fixed about their central axes, or fixed to their central axes, so they can't. We don't have any kind of translational momentum. And more importantly, that axis will be at a point. Is at the center of mass of the gears. So previously we looked at a case of a swinging bar that was hung from its top, and in that case, even though it was a rotating object attached to a single point, we still had to worry about linear momentum because the bar was not rotating about its center of mass. But here the center of mass will not be moving. So we will draw impulse momentum diagrams for each gear. All right, so let's say this. I'm going to draw out the big disk first, or big gear, gear A. And I'll draw 3 of these. The first will represent the initial angular momentum. The second will represent the third will represent the final angular momentum, and the middle will represent the impulse. The middle will represent the impulse. And the first thing I want to do is draw out the, let me label this circle, the center of each of these. And this plus this is going to equal this. This is initial momentum. Plus impulse is going to equal final momentum. Will equal final momentum. And the initial momentum here is going to be IA times omega A 1, or initial, which is equal to 0. So again, angular momentum is equal to, we of course know angular momentum is equal to the moment of inertia times the angular velocity. And however, this thing is starting from rest, so its initial angular velocity is 0. Then looking at the, there are going to be 3 forces on this thing. There's going to be AXT, the X support, if there is any from the support. It's a pin support, so, or it literally is a pin. So the impulse would just be that force, which is AX times T. And then the Y, the impulse from this would be AY times T. However, these don't really do anything to actually contribute to the momentum in the system, since they cannot contribute to the rotation, since they're angular, since they have a moment arm of 0. And again, this is a YT. AY times T. And then I need to take into account the tangential force, and that here I have a tangential force. This is the contact force between the 2 gears, and this will be, let's just say, I'll just call that force F, and then times T. And then in the end, what this will equal is simply IA, moment of inertia of disk A, times the angular velocity of A, omega A, at point 2, or at time 2. And we don't know that yet, but we'll figure that out in a second. Then let me draw out the small gear. So this all is gear A. the large gear. And then the small gear, gear B, will be this series of diagrams here. But the same kind of thing will apply. The initial angular momentum plus any impulse will equal the final angular momentum. And we would also, as a reminder, put any kind of translational momentum if we had that in this, on these diagrams. If we had it, we would also apply any kind of translational momentum that was present, but that's not present here, so we don't have to worry about it. So, and again, this plus this equals this. This is initial momentum. Initial momentum plus impulse yields final momentum. Yields final momentum. All right, so I'm going to have IB omega B at time 2 plus the forces here times the forces on the impulses here. See, the one impulse will be the tangential force. That is going to be F times T. It's the same force here, but do keep in mind, what am I doing in terms of the directions of these? They need to be equal and opposite, yes. So as long as we still believe in the laws of dynamics, as long as we still fear Newton's ghost, whenever we draw a set of forces, we need to make sure to draw them in equal and opposite pairs. I don't know why you would fear Newton's ghost, but I suppose you could. Anyway, and then the rotational impulse here will simply be m times t. That is the moment that will be applied to this thing. And then we'll have the two reaction forces, by times t and bx times t, although we know these are not going to contribute to the rotation because they pass through the axis of rotation. It would be to try to get those to produce any kind of change in angular momentum would be like trying to push on a door by pushing on the hinge.
Why did it add it if it's not going to make any change?
Why? Okay, the question is, why do I add it if it's not going to make any change? For the sake of completion. For the sake of completion. So I do want to draw all the forces on there, but just for the sake of completion. Although we probably could ignore them, just like I don't have the weight on here. But anyway. And then the final angular momentum will be IB times omega B 2. Omega B 2. Okay? So then I just want to work through some equations from this. I just want to set up some equations, mainly via summing moments about each of these. Okay, I'm going to do a balance of moments on each case, and also a balance of momentum. So consider gear 1, or consider gear A. Well, gear A. So again, I know that the angular momentum 1 plus the impulse will equal the angular momentum 2. So let's consider this. And let's say 0, if I sum moments about the origin, or about the axis, I can get that 0 minus FTR, FTRA, and I'll explain what that means and where this is coming from in a second, is equal to negative IA times omega A 2. This is the initial angular momentum, this is the final angular momentum. And notice I assumed basically that this one, because this moment here is counterclockwise, I'm assuming that gear B will be moving counterclockwise, which it has to. And if gear B is moving counterclockwise, then gear A has to move counterclockwise. And that is why I gave it a negative sign. And the moment then for the force here, I needed to translate that force into an angular rotation. And we do this by taking, if I want to translate that force into a moment, I multiply F times its radius times the moment arm there. And then it's just the same times T. Then I can say if I solve this, I can say that Ft, if I put in the radius, Ft times a radius of 0.250 meters is going to be equal to the formula for the moment of inertia of a disk, which if we calculate the moment of inertia here, let me see something here. Let's see. Yeah, that is fine. Let me look at something here. Yes, that's what I thought. See, okay. Well, if you go and use the formula for, if you use both the moment of inertia if you use both the mass and the radius of gyration, you can find the moment of inertia of this thing, of gear A, is going to be 0.400 kilogram meters times omega A 2, the second omega A, the final omega A, I should say. And then, however, let's think about this. Let us consider this here. Now, if you find the angular momentum that or the angular velocity that corresponds to RPM, let's consider this here for a second. Let's see, how would I mention this? Well, I know that, so let's just put that on the shelf for a while. And then if I sum moments about axis, again, this would be on A. Then if I sum moments about B, the same kind of thing. If I sum moments about B, I get 0 plus mt, 0 plus mt minus f t times the radius of gear B. It's going to be the same force, except some things will be positive instead of negative. And then this m is the applied moment, equals IB times omega B final, omega B2. Omega B2. Then I can put in some known values. This m is 6 Newton meters. Time is just the unknown time that we're solving for. Minus ft omega b here. Minus ft omega b, let's say ft times the radius, again, which is going to be 0.100 meters. 0.1 meters here. And then the moment of inertia, if you calculate the moment of inertia, it will be 0.0192 kilogram meter squared. And then the final, then we can say omega b2, the final angular velocity. Now, if you go and calculate the angular velocity, we do actually know the final angular velocity. 600 RPM, that is going to be the final, if you remember from the problem statement, that is the initial angular velocity of gear B. And that leads to if omega B equals 600 RPM, that means that omega B, I should want to be consistent and say omega B2 is 600 RPM. And that corresponds to a value of, let's say that is 62.8 radians per second. 62.8 radians per second. And then if you do a simple conversion, if we say 62.8 RPM, omega A times 2, or not times 2, the second omega A, the final omega A, is going to be 62.8 times, this is the, again, the radius, this is going to be the, okay, so how can we calculate omega b? Well, think about this. I know that basically VA is equal to VB, is it not? At the point of contact, the linear velocity of A must be equal to the linear velocity of B, and I know that RA omega A is equal to RB omega B, because the linear velocity is just equal to the angular velocity times the radius, and that leads us to that omega A is going to be equal to RB omega B divided by, let's say, RA. So if I put in the radius of B, the radius of A, and the 62.8 radians per second squared, I get that omega A is going to be 25.1 radians per second, not radians per second squared, sorry, just radians per second. So then working through this some more, I can, if I then substitute those values in and multiply for gear A, I get that Ft is equal to 40.2 Newton seconds, and the equation for gear B collapses to an equation that says 6 Newton meter T minus Ft minus 0.1 Ft is equal to, let's do 0.192 times 62.8. My only unknowns are T and F, and same F and T, and if I solve these systems, solve these equations, very basic algebra, I will find something, and I will find that the time is going to be very quick. It's only 0.871 seconds, 871 seconds, and the force, the F, is going to be 46.2 newtons. 46.2 newtons, and those are my final values for the system. Again, in summary, what did we do with this? Well, we went and constructed momentum and impulse diagrams. We looked at the initial angular momentum, we looked at the final angular momentum, we included in our drawings any forces on there. And now if you are looking at a purely rotational system and you don't have any kind of, and you have some forces on there that are acting through the center, you don't really need, or acting through the mass center, in that case it's not particularly important to include those forces, but for the sake of completion you can. But in general, we're going to be looking at all of the forces there. So again, we set up a diagram, we set up the diagram of initial angular momentum, final angular momentum, and any impulses on there, and then work through our algebra from there. Yes?
And, some of the while calculating for the work for U1 to 2, I realized that some of them, when you're searching for the angle, they attach it to the moment. Then sometimes when you're trying to get time, you also say mt, sometimes say m theta.
When would you use the angle? So the question is asked, sometimes when solving for the work, you use the angle, you use the theta. Well, that would obviously be a, just like force, like work is equal to F delta T, right? Well, you know, we saw a similar equation with moment and theta was applied for work, right? For work in a rotational sense, or rotational work, shaft work. And so that's when you're going to use it. If you're doing a work problem, you'll have that kind of theta. Here, if you're doing an impulse, you can also have the theta there. Does that?
What about time? Well, sometimes I saw some of them, they also added.
We'll typically not use time for a work problem. You may sometimes, if you're asked for time, you have to go and back calculate it. But by definition, when applying energy methods, we're not really going to use time. By definition, now you may after working through the energy portion of it, you might go and use the information you got and apply some kinematics or something. But by definition, I'll just note on energy methods, an aside on energy methods. A key term for energy methods is they are path independent. In other words, like consider the case of the, I mean, if I look at a simpler case, something you saw in, like high school or something like that. If you have a case, remember the old roller coaster problem where there's a roller coaster that goes through a series of hills and loop-de-loops and everything else, and there's a cart on a track that goes down, and I give you the height here. I give it you initial velocity, or I say it's released from rest, and then I tell you how what h1 is and what h2 is. I tell you these, and then I ask you what is v2. Right? Remember that type of problem? This type of energy method problem. Well, when I say path independent, I mean that as long as this is if I say the track is frictionless, it doesn't matter how long this track is. Now, if it's, the thing is, when I say it's frictionless, that I'm saying that there are no non-conservative forces. In other words, as I go along this track, I'll be continually exchanging kinetic for potential energy. But at no part does the object itself, the cart, actually lose energy, right? That is what it means to be in a conservative system. A non-conservative force will be losing energy all along the way. However, one of the neat things about that, about being path independent, is that I only need to know the system here and the system here. I don't need to know anything about what is going on here. There could be 1 loop or 1,000 loops. However, we do lose something in that kind of path independent problem, and what we lose is time. What we lose is time. See, if I truly had a zero friction surface, imagine I had some crazy, to do this in real life, you'd have to do something really crazy like a vacuum train kind of thing. There's a vacuum tube, all the air is sucked out of it, and it's the car chassis itself is on magnetically levitated bearings, that kind of thing, right? And if you had the system like that was almost zero energy losses, I could have that track be 1,000 miles long. I could have it go in all sorts of loop-de-loops and all sorts of different directions, and it would just keep on going as long as there was no friction. If there was no friction, if there was no air losses, it would just keep going for days, wouldn't it? But the problem is, with those energy methods, I can tell you, if you tell me the height and the initial velocity, I can tell you the height. If you tell me the height here, I can tell you the final velocity. But I have no idea how long it took to get there. If all I know is the initial state and the final state, when I'm drawing this out, I'm not actually trying to, when I drew this problem out, I wasn't trying to make sure that I made the loops, this many feet high. I'm trying to say high and tall at the same time. This many feet tall, and this one, this radius and everything else. It could be, depending on the specifics, this could be 10 minutes later or 2 minutes later or 1,000 years later. We don't know anything about it. So energy methods by themselves don't tell you anything about the time. Now, sometimes you could go back and, make some assumptions and apply momentum or kinematics, etc. But in terms of energy methods by themselves, you cannot get anything time related therein. Or, so for example, if we looked at this from an energy point of view, we could say, okay, well, we could find the amount of work done by the force. We could find the work done by the force and find its final kinetic energy, final rotational kinetic energy, look at the balance therein. And then we could apply some rotational kinematics to say how long it took then to find the time. But we're not using the energy method itself to find the time. We're using kinematics, or we're using impulse or whatever. So does that kind of answer that question? Okay. Hopefully that wasn't too far off on a tangent, which I sometimes do. Anyway. All right, so let's work through another case here. All right. Okay, consider a uniform sphere of mass m. So consider this here. There is a sphere, a ball. So example 2 here. And I have a center of mass here, And the initial velocity or the initial momentum is going to be purely linear. Will be purely linear. So this thing has an initial velocity of v1, or v bar 1 if we prefer to show it's the center of mass average velocity. And the idea here is that I'm taking this ball and throwing it horizontally. And at some point it is going to come in contact with the ground. And I want to start analyzing it from the point of view of it getting in contact with the ground. And initially it's going to be sliding. Initially when it first hits the ground it has no rotational momentum, and eventually then it's going to start sliding. But it's not frictionless. The ground has a coefficient of kinetic friction of mu kinetic between it and the ball, mu kinetic. And so again, this thing is going to have a mass m and radius r, sphere, mass m, radius r, and radius r initially slides along the ground. Initially slides along the ground. Initially slides along the ground with no angular velocity. With no, or we could also say with no rotational momentum. With no rotational momentum. Okay, so I wanted to determine a few things. Determine or find the time t2. So it's going to strike at some t1, I suppose. The time t2, where the ball starts rolling without slipping. Where the ball starts rolling without sliding. This is A. And B, the linear and angular velocities of the sphere at time 2. And we're going to do this all in terms of the variables r, m, etc. Linear and angular velocity of sphere at time 2. At time t2. At time t2. Okay? So again, what is our first step going to be? Yep, we're going to draw momentum and impulse diagram. So initial momentum diagram, so an initial momentum diagram, an impulse diagram, and a final momentum diagram. All right, so let's do that. Let's do that thing I said. And I'm going to designate the point of contact, point C. So let us consider that here. I have my center of gravity here. And the initial momentum is just going to be, the initial linear momentum is going to be mv1, m v bar 1. And I'm going to label 2 points, G and C. G will be the, will be the center of gravity, and C will be the point of contact. Then this, so this plus, and I'll also make a point to mention that the angular momentum here, I omega 1 is 0. Omega 1 is 0. Initially, it's just sliding along the ground. It doesn't at the point of contact. It only has linear momentum and no angular momentum of any kind. It will gain angular momentum through its rotation. Through its rotation. So here is point C and G. And let us consider the forces on here. Well, I don't have any torque, raw torque applied to the ball, but I do have weight acting down through the mass center. I have the normal force. I'll just use N for now, normal force N. And then I'll just let this force F be the frictional force. And of course, all of these are times T, NT, FT, that'll be my frictional force, and then WT for the impulse of the weight. Although in this case, that's not going to do anything because that is acting through the center, although it will help generate, it is what will generate the normal force. And then this will equal the final momentum, both linear and angular. And the final angular momentum will be some I omega 2 and an M V2. MV2. All right. So this is our basic, again, this is initial momentum. Let me do this in a different color. We'll have initial momentum, impulse, and final momentum. So initial momentum, impulse, and final momentum. And final momentum. Now let us work through the equations. Let's see. Let's consider this. Okay, so let's work through this. So the first thing I'm going to do is sum forces in the x direction on the impulse diagram, or sorry, sum forces in the y direction on the impulse diagram. And this is going to be NT, or really summing momentums if I really want to think about it, or sorry, if I'm really summing impulses. NT minus WT is equal to 0, so therefore N, the normal force, is going to be equal to the weight W, which is just equal to mg. So the normal force is equal to mg. Summing, let me say fyt, summing fx times t. This is going to be mv1 minus ft, the frictional force, equals mv2. So again, we're summing across all of the components, all of the diagrams. Here, if I sum everything in the y direction, I get only this and this. However, if I sum in the x direction, I'll have this and this present, as well as the frictional force there. So mv1 minus ft is equal to mv2. Then putting in comparable pieces, mv1 minus, well, I can replace this with F, again, is going to be equal to mu kinetic times the normal force. That's the term for the frictional force. Or I could also say this is equal to mu times m times g. So minus mu kinetic, the coefficient of kinetic friction, times m times g times t is going to be equal to mv2. And this tells me then that v2 is equal to v1 minus mu kinetic gt. Mu kinetic times the acceleration due to gravity times time. Then if I do a sum of moments about the center of mass, about g, so times the sum of moments about g, or the sum of moments about g, if we consider here, what will we have? Well, we will not have any angular momentum on this piece, on the initial diagram. However, this one, the N and the weight will not generate any torque. They have no moment arms, so they will not generate any moment about G, or their lines of action pass through G is a better way to put it. And Ft, however, will generate a moment because it has it's entirely perpendicular. Its line of action is perpendicular to the radius, so it will definitely generate a lot of torque. So again, keeping in mind appropriate directions, I have FTR the moment of that force times its impulse, times t to get an impulse, equals I omega 2. I times omega 2. And if I then put in this here, F, again substituting F for mu mg, I get mu kinetic mg times r, or mu kinetic mg times tr. And then if I want to put in the expression for the moment of inertia of a sphere, and that is 2/5 mr squared, 2/5 mr squared times omega 2. And then I find that omega 2 is equal, if I solve this for omega 2, I get that omega 2 is 5/2 mu kinetic times g divided by r times t. Mu kinetic times g divided by r times t. All right, then the only thing left to do is apply some basic kinematics and solve for t. So if I know by definition of my relation of linear and rotational velocity that v2 is going to be equal to r omega 2, r times omega 2, and that v1, and then for my previous equation, I know that v1 is equal to mu kinetic, or v1 minus, what might I say here? Well, let me go back to this here. First, let me modify this a bit. I'm going to go back to my v2 equals v1 minus mu kinetic times g times t here. And if I look at this from the other point of view, I could also say, if I flip this around, v1 equals, let's see here. v1 equals, or v1, let me be consistent here, minus mu kinetic gt is equal to v2, which is equal to r omega 2. And if I replace omega 2 with my expression here for omega 2, I can have this reduced to v1 minus mu kinetic gt is equal to r times 5/2 times mu kinetic g over r times t. And if I go then and solve this for v1, or I solve this for t, sorry, I have this t is what I'm after, I'll find that t is equal to 2/7 times v1, the initial velocity, divided by mu kinetic times g. So it is dependent on the initial velocity, and again, this is the amount of time that it's going to take for this thing to accelerate enough, or get enough angular velocity, or spin up enough, if you prefer, to the point where it has it is able to roll. It has sufficient angular velocity to roll along the ground without any slipping. All right, so I think then that we might take a break there, then come back, look through another example or two, and then look at the final topic for the chapter, and that is eccentric impacts. All right, and thank you.